Thank you very much for having me in this method series. It's a real honor to be here. So yes, as Camila said, I'm going to be talking about actually an area that intersects these two interests of mine of missing data and causal inference. So it's about the use of missingness DAGs to guide the treatment of multivariable missing data. And so I'm going to just jump right away into it. Yeah. So here's the outline of my talk, just to give you an idea of where we're going. So I'll start with the background and rationale, and I'll spend a fair bit amount of time here, just since I imagine not everyone is in the depths of missing data literature, just to really motivate and explain what the rationale of this work was. So I'll start with a motivating example. I'll give a brief overview of developments in missing data methods and the current challenges with multivariable missingness, which we continue to face in practice. Then I'll go on to talk about a roadmap to handling missing data that uses missingness DAGs to depict assumptions, and also cover, well, the key things are missingness DAGs and the concept of recoverability of the estimate of interest and how to use these two things to determine the best approach to handle missing data. And then we'll finish with some brief conclusion and discussion and hopefully some questions. So the motivating example is based on a study that was aiming to answer the following question. So in females, what is the average causal effect of frequent cannabis use in adolescence on mental health in young adulthood? And this was a study published in the BMJ, that date is wrong, sorry, not in 2022, more in the early 2000s. And it was using data from the Victorian Adolescent Health Cohort Study, which is a population-based longitudinal cohort study of around 2,000 adolescents. 1,000 of them were females, who were recruited when they were 14, 15 years of age back in 1992, 1993. And they have been followed for 11 waves, but we'll focus on the first 7 waves in this case. So that initial study focused on those waves. So first, there were some adolescent surveys conducted every 6 months, which collected a range of exposures and factors. And here is where we'll draw our data for the exposure. So we'll basically use a cumulative exposure measure and treat it as a point exposure, which is what the authors of that study did, and sort of forget for a minute about all the complexity with time varying exposures, and just to introduce this these other concepts. And then in wave 7, when they were around 20 and 21 years old, it's when the outcome was collected on their mental health. So just to give you a bit of a better idea of this, so I'll introduce the notation. So the exposure will be X, the outcome Y. And so the exposure was self-reported frequent cannabis use during all those adolescent waves, and we've dichotomized it to yes, no, if they did report it at any wave. And the same as in the published study, we were trying to keep it sort of similar to that. And then the outcome was a mental health score in young adulthood, which was a continuous score. And then we have some confounders, some of which were complete. So the parent completion of high school, parental divorce or separation, and antisocial behavior in adolescence, and some confounders which were incomplete, so mental health in adolescence and alcohol use in adolescence. All of them are binary. It's probably a bit of a simplification, but I guess it's sort of a slightly simplified case study to focus on the aspects of missing data. And the estimate of interest, as I mentioned at the beginning, is the average causal effect, which is the mean mental health score had everyone been said to receive the exposure versus if had they been said to not receive the exposure. All right, so in the case where we have complete data, we can draw a causal diagram that depicts these assumptions that we have around these confounders being sufficient to adjust for confounding. So the exchangeability of assumption that we would use is telling us essentially that by conditioning on these confounders that I listed, those 5 variables, here are the complete ones, here are the incomplete ones, then we are blocking all backdoor paths between the exposure and the outcome. That's what that assumption is. And we've just, for simplicity, separated the complete and the incomplete confounders, which we need to do so for our later purposes. All right, so we refer to that as the CDAG, the complete data DAG. Now, as I mentioned, obviously this study had missing data, and it's very common in cohort studies like this that there's missing data in almost all your analysis variables. So in this case, there was missing data in the exposure, the outcome, and the two incomplete confounders. So obviously, by definition, there was no missing data in the complete confounders. But overall, there were 35% of records which had data missing in any of the analysis variables. And we actually deleted 39 records with missing data in a few of these confounders to really have these as complete to simplify. So this resulted in a sample size of 961. All right, so what do we do when we have missing data? So just briefly, what are the sort of simple, easy approaches that one might think of doing? So the complete case analysis corresponds to deleting records with any missing value in analysis variables, which is the default in software. And so pitfalls of this would be possible bias if there are incomplete records, if incomplete and complete records differ, and loss of precision because you're discarding 35% of the records. You could think of doing single imputation. So, for example, replace missing values with an estimated value, such as the mean or the most common value, and analyze the data set as if it were complete. And pitfalls of such an approach would be possible bias, again, if there's a difference between these incomplete records in terms of observed or unobserved variables. And there's also an underestimation of bias when we're doing single imputation and treating those values as if they were truly observed. Then there's the missingness indicator approach, which is often used to handle missing data in confounders. For example, put like a missing category when you have a categorical confounder. But it has been shown that this approach is subject to bias when some very strong causal and parametric assumptions are violated. So these sort of approaches could be okay in certain cases, but to understand what cases that might be in terms of bias specifically, we need to consider the assumptions about the missingness mechanism, which Rubin sort of alluded to in his paper in 1976. And the missingness mechanism is essentially the causal process that is leading to missing data. So following that work, Rubin proposed a classification of missing data mechanisms, which remains to date very, very used and mentioned. So in the setting of one incomplete variable, for example, if only the outcome were missing in the VAX case study, we have the assumption of missing completely at random, and that is when the probability of a value being missing is independent of the value. So in the case of the VAX example, it would mean that the probability of the young adult mental health score, which is the outcome, is missing, is independent of the young adult mental health score. The data would be missing at random if the probability of that value being missing is independent of the value given the values of other variables, which in this case with one incomplete variable are all completely observed. So the probability of young adult mental health score being missing is independent of the young adult mental health score given adolescent health. That would be an example in the VAX example. And then finally, the data is said to be missing not at random if the data are not missing at random. And that would be the case, for example, if even given all the measured variables, the young adult mental health score being missing is still dependent on the value, for example, because your mental health is affecting directly your willingness or capacity to complete this questionnaire. So that's in the setting of one incomplete variable. But what I just described is really what people have in their head of what these things mean. But we'll see later that it's a little bit more complicated with multiple incomplete variables. And if you think about it, then mathematically, it was shown that the complete case analysis is only guaranteed to be unbiased for the joint distribution of all the variables under the missing completely at random assumption, which is a very strong assumption. So the realization of all these things back in the 70s, 80s, led to the development of what are known as like MAR methods. So, for example, there's full information maximum likelihood. It's when you fit a model to all the variables, a joint model using maximum likelihood. And it can be shown that such an approach can be unbiased for the joint distribution under missing at random if there's an additional assumption about the model parameters that holds. Then multiple imputation was proposed, which I call MI, and you will see that abbreviation throughout the talk, MI, which is when the data are multiply imputed from a carefully constructed model, and then all those different data sets analyzed, and then the results combined using Rubin's rules. And that approach is guaranteed to be unbiased for the joint distribution under missing at random. And it's superior to single imputation because it incorporates that uncertainty regarding the imputations. And then inverse probability weighting, which is when the analysis is weighted by the inverse of the probability of the data being missing. So it's unbiased it has been shown to be unbiased for specific parameters, such as the conditional outcome expectation, regression coefficients, etc., under that missing at random assumption. So with the higher availability of software, these sort of MAR methods have become easier to implement, and so they have become more commonplace. And I would say especially multiple imputation, because there has been a lot of, I guess, development and implementation in software of methods that can handle very general multivariable missingness mechanisms. But as often happens when things are so easy to apply, we forget which are the situations where we can use them. And the use of all these MAR methods really depends on that MAR assumption being plausible. So now let's go on to consider the setting with multiple incomplete variables. And a really nice paper by Sean Seaman in 2013 clarified that the assumption that is needed by these full information maximum likelihood and MI methods is really what he terms everywhere MAR, which is which means that across repeated samples, the probability of a missingness pattern is independent of the values that are missing in that pattern, given values not missing in the pattern. So just to exemplify this with the VAX example, to make it a bit clearer, let's imagine that we only have 4 variables, so 3 here that are incomplete and 1 that's complete. So we have 8 possible missingness patterns, so it means whether a variable is complete or not. In this table, I have 3 examples of the patterns out of those 8. So 1 means the variable is observed, and 0 means it's missing in that pattern. So in this pattern is where only young adult mental health is missing. In this pattern is where the exposure is the only variable missing. And in this pattern, we have the exposure and one of the confounders missing. So what everywhere MAR means, which is the MAR assumption that needs to hold for MI to be guaranteed to be unbiased, is saying that across repeated samples, the probability of a given pattern doesn't depend on the values of the variables that are missing in that pattern. So for pattern 2 here, the probability of the pattern occurring cannot depend on the outcome. For this second pattern here, it cannot depend on the exposure. And for this third pattern here, it cannot depend on the exposure and this confounder, right? So it's a little bit more complex than how it's usually phrased in words. So this sort of leads us to the challenges that arise with multiple incomplete variables in practice. So the first challenge is that this everywhere MAR assumption remains really poorly understood. Its plausibility is really difficult to access in real settings. Imagine settings where you have, 14 confounders and most of them have missing data, and you have the outcome exposure, and so you need to think about all these patterns and how are you going to assess this. And it does seem to become increasingly stringent as the number of incomplete variables increases, because you have more and more conditions that need to hold. The second challenge is that contrary to what is, so people really tend to connect MI is an MAR method, complete case analysis is under missing completely at random. There seems to be this understanding that there's a one-to-one correspondence between the assumption and the methods that enable unbiased estimation. But especially when we focus on a target estimate like the average causal effect, specific target estimate rather than the whole joint distribution, it is easy to show that missing completely random may be sufficient, but it's not necessary for complete case analysis to be unbiased. And similarly, missing at random is sufficient, but not necessary for MI to be unbiased. So, but these sort of issues in practice, the fact that MAR is not well understood and the fact that there's not that one-to-one correspondence in the setting with multiple incomplete variables, really has led us to the current state of practice, which I see as being an indiscriminate use of these methods, especially complete case analysis and MI, because it's very widely accessible, as I mentioned, with little consideration for what the target estimate is, and then more specifically what the plausibility of the missingness assumptions and what they imply in terms of identifiability of the estimate, with most studies really either not mentioning assumptions or claiming we assume MAR but don't give any justification. And we actually show that in a scope and review of the reporting, the use of reporting of MI in the literature. And then what these two things mean in terms of the best estimation for the estimate given the missingness assumptions. And in particular, when to conduct sensitivity analysis using so-called delta adjustment approaches, which are basically like bias analysis approaches. They are widely recommended in all the missing data guidelines, but they are very difficult to conduct, and it's really unclear when they should be conducted because there's really not a good understanding of the assumptions. So the result is obviously a choice of analytic approaches that may be inappropriate and an inappropriate interpretation of findings as a result of that. And I really think that this is more reflective of a broader lack of consideration of these three steps in practice, in statistical practice, of consideration of estimate, consideration of assumptions and identifiability, and then based on that, choose a method, because practice has tended to overemphasize estimation procedures like regression. We have a paper with my colleague on the use and abuse of regression that may be of interest. But same thing with MI and complete case analysis and all of that is just emphasis on what is the method that is going to solve my problems and forgetting these first two key steps, which are very central to causal inference, but I guess in the more general practice, that still hasn't permeated well enough. So the aim of this talk, now finally, after I went through all the background, is to present, just give you a flavor of a body of work that has sought to develop and translate to practice. Firstly, a roadmap for handling missing data that is grounded on those three key steps. So considering the estimate, defined in a non-parametric way, so not based on a parametric model, the assumptions and the recoverability, which is how we talk about non-parametric identifiability in the missing data literature, and what are the estimation approaches. I in particular really focused on the use of missingness DAGs for that second step of the assumptions as an alternative to this MCAR, MAR, MNAR classification in order to specify and assess assumptions in the multivariable setting and to understand what they imply in terms of recoverability to guide analytic decisions. And this body of work is not just my own, so this is my whole team involved in several work that we've done on this. So Jajin, who was a PhD student of mine, now a postdoc in my team, Kate, with whom I co-lead the missing data team, Ghazali, Katram, early career researchers, and John and Julie. So thanks to all of them for all the work on this. It's not just my work that I'm presenting. All right, so we're going to start with the roadmap, and then I'll take you through the roadmap with the example to give you a flavor. But as I said, there's a number of papers, and I'm going to show them at the end that if you want to learn more, you can go and read. So the first step of the roadmap is to define the target estimate and the analysis that would be conducted in the absence of missing data. Second, third steps are all about assumptions and recoverability. So drawing a missingness DAG to depict missingness assumptions and then determining the recoverability of the estimate given the m-DAG. And then finally determining and conducting an appropriate approach for handling missing data in the primary analysis based on the recoverability. And then a fifth step is to acknowledge that we often have an uncertainty about the m-DAG and conducting a sensitivity analysis to reflect that uncertainty. All right, so the first step in the VAX example, so I had mentioned the estimate is the average causal effect. And if we can assume throughout the talk the usual assumptions of consistency, positivity, conditional exchangeability given set 1 and set 2, which we depicted here in that c-DAG that I showed before. And we additionally assume no effect modification within the strata of the confounders, which means that under further parametric assumptions, the average cause of effect can be shown to be equal to the exposure regression coefficient in a simple outcome regression model, which includes the confounders as well. So that's the simple setting we're going to take in this, the rest of the talk. So the next step is to draw an m-DAG to depict the missingness assumptions. So an m-DAG is a DAG that is extended to include variable-specific missingness indicators. So this is distinct to a set DAGs where you include a complete case indicator, which has been the basis of a lot of work as well out there, such as that paper by Rhea and Daniel from 2011. And so in the VAX example, the m-DAG is going to include missingness indicator for the exposure, a missingness indicator for the outcome, and it could include a missingness indicator for each confounder separately. In the rest of the talk, for simplicity, I'm just going to use one missingness indicator for missingness in any confounder. And that already leads to a lot of complexities with m-DAGs. But I guess you could also just do it separate. But it's just to show the concepts and to really simplify it in practice, I think, as well. So in the VAX example, a trivial missingness DAG is just, we have the c-DAG that we had before, and now we have 3 missingness indicators, one for the confounders, one for the exposure, one for the outcome. And we can assume that they are all correlated via, for example, unmeasured common causes of missingness, like behavioral traits. Maybe there is a common trait not to answer questionnaires, for example. And in this trivial m-DAG, where there are no arrows connecting the c-DAG variables with the missingness indicators, the assumption is very strong, obviously, is that the only cause of missingness is W, which are those unmeasured factors, and it's not related to any analysis variable. Obviously, that's very strong. So we'll move on to more realistic DAGs in a minute. But before that, I'll just talk a little bit briefly about how these m-DAGs have been developed in the literature. So really, they were proposed and the theory developed by Kartika Mohan, who was a PhD student of Julia Perro, in a range of large body of work and really interesting. And one of the things that they did was also to propose equivalents for the missing complete random MAR and MNAR, like graphical equivalents for those assumptions. I was, as a postdoc here, working at the time, and I found that really interesting, and I really wanted to see how we could use those in epidemiology. And so I started to work on constructing like typical m-DAGs in this point exposure setting for epidemiological studies. And that led to some work based on these canonical m-DAGs that I'll talk about later. But one thing that I was keen on was to move beyond a 3-way category and really think about more fine-grained classifications. So that's what the canonical m-DAGs was about, and I'll show you later. Then partly the reason for that was because I thought the MAR equivalent of graphical equivalent of MAR is stronger than MAR, and that sort of led a lot of the missing data people to say, well, but MAR is weaker than that, so why would we use that? So really, I think going beyond that really helped to show what the promise of this framework was in these epidemiological settings. And then after that, there has been various developments, theoretical by Razi and Avi, Tika, who developed an identification algorithm, for example, that I'll mention later. And then there has been some more recent work looking at mediation analysis, time varying exposures, and so on. So it has really started to take off, this work. So going back to the VAX example, so obviously a more sensible thing is to at least allow for the complete confounders to be causes of the missingness indicators. And so in this m-DAG will be allowed for that. And so the assumption is that the complete confounders are also causes of missingness in any of the variables. But then moving from that, we can consider extending this by adding arrows from the incomplete variables, so these 3 nodes here, to the missingness indicators. So for example, here, if we assume that the exposure is a cause of missingness in the outcome, then that's possible, and that actually implies an m-DAG mechanism, because now we have an incomplete variable causing missingness in another variable, which means that in those patterns, the restriction that is needed for everywhere MAR is already violated. So we're already entering m-DAG world in this DAG. Then we can consider another extension, which is when the outcome causes its own missingness, also more obviously an m-DAG mechanism. Anyway, so what we did was to elicit an m-DAG. You will, in this point exposure setting where you take this sort of as your base m-DAG, the idea is to start, if you want to elicit that from experts, to start to think about all these arrows from incomplete variables to the missingness indicators. And that's what we're doing in this table. It's looking at the incomplete variables, and here are the missingness indicators, and sort of showing, based on the literature or expert opinion, whether this arrow is likely to exist. So in this VAX example, this is the exercise was done by Jajin when in this paper in Biometrical Journal. So basically all the arrows are likely except these 2 from the outcome to these other missingness indicators. So it leads us to basically this being the plausible m-DAG. So there are arrows from the incomplete variables to the missingness indicator, from the incomplete confounders, from the exposure to the missingness indicators, and only from the outcome to its own missingness. So that's what we deemed as the plausible m-DAG in this example, based on the literature and expert knowledge. All right, so that leads us to an m-DAG. Then the next step is to determine the recoverability of the estimate given that m-DAG. So what do we mean by recoverability? As I mentioned earlier, it's really just non-parametric identifiability. So it means, formally, it means that if the conditional independencies that are implied by the m-DAG, which can be derived using the separation rules, enable us to mathematically express the estimate as a function of the distribution of the observable data in an infinite sum. So asymptotically. And informally, you can understand it as the fact that we can biasly estimate our estimate based solely on the parameters or associations that are in the observed data without needing to incorporate external information about the distribution of the missing data. So I'll show you a few examples. So for example, going back to this extension of the m-DAG for the VAX example, where we have exposure causing missingness in the outcome, the conditional independence of interest that is implied is that the outcome is independent of all the missingness indicators. So this is just the vector of missingness indicators, given exposure and the confounders, all the confounders. And with this conditional independence, we can show that we can actually express the conditional distribution of the outcome given exposure and confounders as the conditional distribution of the outcome given exposure and confounders in the complete cases. So in all those who have complete records. So that means, because the A's given our in step 1 assumptions is simply a regression coefficient in a model for this variable, that means that the average causal effect is recoverable in this m-DAG, even if we are in an MNAR setting. And it's recoverable by the complete cases. On the other hand, in this simple extension that I had shown you, the conditional independence that's implied is similar, but it doesn't include the missingness indicator for the outcome. And we can actually see that it's not possible to deseparate y from my. And that implies, as shown by several of the results that I'll show you later, that the ACE is not recoverable in this setting. So the question is, so I've shown you what the concept is, but as you can see, determining recoverability is very specific to your m-DAG and the estimate that you have, and it's not trivial in many settings. So it's a bit more of, I guess, a more complex problem than just simple ACE identifiability, because the DAG is changing and the exchangeability conditions required might be changing depending on the DAG and the estimate. But what can we do in practice to get over this obstacle? So there are some things we can do. We can rely on general theorems that as have been developed and proved by Kartika Mohan and Razinavi and co. Part of my rationale for that first piece of work was to develop results for some typical scenarios, those canonical m-DAGs, and then Jiajin extended that to the average causal effect. So we can use those pre-existing results, for example. Or there are, I mentioned the identifiability algorithm developed by Tika, and that was implemented in an R package. So one can also use a software package to prove recoverability. So in terms of the general theorems, some highlights are as follows. So for example, a lemma from Kartika showed that non-recoverable estimates remain non-recoverable in m-DAGs obtained by adding arrows. So if you know that something is not recoverable in an m-DAG, you can assume that all bigger m-DAGs are also like that. They also showed that the marginal distribution of the outcome is not recoverable if y and my are connected, either by a direct arrow or a measured variable, that is a common cause. And then they also showed that the conditional distribution of the outcome given a set of variables is not recoverable if y and my are connected either directly, again by an unmeasured common cause, or if one of these variables is a collider. And in our example of BAGs, because we have an arrow from the outcome to the missingness in the outcome, we know that therefore by this corollary, this conditional distribution is not recoverable, and therefore the average causal effect is not recoverable. Now moving on to the second part, the canonical m-DAGs. So what I mentioned was that I was trying to sort of organize the m-DAGs for this point exposure setting. So I started with this base m-DAG and considered all possible extensions that arose by adding any of these purple arrows, which leads to 512 possible m-DAGs, and then organize them into 16 classes based on characteristics that were important for recoverability of the joint and the outcome distributions. And then I picked the most general m-DAG of the class as the canonical representative, and then derived recoverability for some specific parameters that I'll show in the next slide. But essentially, you can sort of map your, if you're in a point exposure study, your c-DAG will look as the one that I showed, well, barring any other issues like measurement error or other selection bias issues. And then based on which of those purple arrows you consider plausible, it can be mapped to one of these classes. If at least one of, you have to find the smallest DAG that contains your DAG, basically. So in the case of the VAX example, there's one that's identical to the one that we consider plausible in the VAX examples, which is this one, m-DAG J3. So then we can use those pre-existing results to derive recoverability. So in that paper, I looked, which has a correction published this year, I looked at the joint distribution, the exposure distribution, and the outcome distribution, and the conditional outcome distribution. So based on that, the average causal effect, we can also derive that the average causal effect is not recoverable because it's not recoverable under that canonical m-DAG. And then, as I mentioned, Jiajin extended this work to look at the average causal effect in 10 of those m-DAGs, assuming there was no unmeasured common cause of the missingness indicators. And then finally, here's an example of how you could use the R package to search as well. To do this, you use the DAGID library to define your m-DAG, and then use the do search function to check identifiability. If it's identifiable, it will find it. If it's not identifiable, it doesn't actually mean it's not identifiable. It just means that it cannot solve it through that algorithm because it's not a complete algorithm. So if it doesn't find a solution, it doesn't mean there isn't a solution. But if it finds it, it's right. So that's just a little caveat for that. But anyway, all this shows you that there's some progress that can be made in practice to bring this concept into practice. Okay, and finally, we are in the estimation step. So now, based on m-DAG recoverability results, we need to determine and conduct an appropriate approach for handling the missing data. So when planning this, we need to consider the recoverability of the target estimate given the m-DAG. If the estimate is recoverable, then what is the recoverability expression? So how is it that we were able to express the estimate as a function of the observable data? And then the availability of non-harmful auxiliary variables that are not required for recoverability. So I'll talk about the last 2 points in the next 2 slides. So by recoverability expression, I mean this, like going back to that extension 1, I had shown you that we could express the conditional outcome distribution as a function of the observable data in this way. And that's the recoverability expression. And in this case, it's showing us that a complete case analysis would be unbiased. In terms of auxiliary variables, they are correlates of incomplete variables that are not involved in the analysis that you would have conducted had you had no missing data. So what do you define in the first step? And there is a special case. If there are also correlates of missingness in any variable, then you should also put them on your m-DAG and consider them as observable data in your determination of recoverability. So why should we consider these auxiliary variables? Firstly, they may help to improve precision. For example, they can be used in multiple imputation for that purpose. But also when you include it in the m-DAG, they may reveal variables that are actually required to block a path, for example, an open path for recoverability. And they may also reveal variables that are harmful and should be avoided in the analysis, for example, because they are collider and they actually open a path if you include them in your analysis. So it's important to consider auxiliary variables for all these reasons when dealing with missing data. So based on these sort of considerations, here's a pragmatic decision tree sort of to guide us on where to go from here. So you start with wondering, is the estimate recoverable? And if it's not, this actually means that you need to, the data that you have is not enough for you to obtain a biased estimation. You need to conduct a bias analysis that includes external information on how the missing data may be different to your observed data. And a possible approach is the so-called delta adjustment approaches within MI. This is sort of equivalent to when you say, I'm sure there's an unmeasured confounder, and so now I need to conduct a bias analysis. It's sort of a similar situation. But if the estimate is recoverable, then do you have the recoverability expression? You may not, because sometimes you just rely on a general theorem. But if you do, and it shows that the complete case is unbiased, then if it doesn't, then it means that you need to use some other approach that could be based on that recoverability expression, or being pragmatic, you may use something like multiple imputation, for example, or any other approach that you can use to include auxiliary variables that may be required in that recoverability expression or to improve precision. But if it does show that the complete case is unbiased, then the next question is, are there any non-harmful auxiliary variables that could improve precision, in which case maybe you still want to do MI, or if not, then maybe you can just use a complete case analysis. This is not perfect because this, I guess there's still a lot of work to do here, as I'll mention in a few slides, but basically there's no, by letting go of everywhere MAR, we've let go of the theorem that told us if MAR holds, then MI is unbiased. We no longer know exactly when MI is going to be unbiased. So there's work to do here, and essentially also each recoverability expression may suggest a slightly different sort of estimator that would have to be constructed for this specific case, which is very complex to expect to do, which is why I said pragmatically maybe we still use multiple imputation in those settings, and it has been shown to be approximately unbiased in many of those settings. All right, and then final point before I am almost done, the sensitivity analysis to the assumptions depicted by the m-DAG. Essentially, this just means do some other analysis based on some other m-DAGs that you consider plausible. So repeat steps 3 and 4 under your alternative m-DAG and compare the results and use this to inform your overall conclusions. Because it's really hard to be really certain about your m-DAG in most applications. All right, so just to conclude, so in this talk, I presented and illustrated a roadmap for handling missing data that is grounded on the use of m-DAGs and the concept of recoverability to guide analytic decisions. Some advantages of the framework are that it facilitates the assessment of the plausibility of missingness assumption, which is currently really hard for the MAR framework, and also understand the statistical implications of those assumptions to guide analytic decisions. Some limitations are that, as we know, effect modification cannot be portrayed in m-DAGs and yet can have really important impacts in terms of selection bias. And then also, as I was saying, there's no overarching theorem that links m-DAGs with estimation approaches, in particular MI. So that makes it a bit difficult. But the approach has led to insights that challenge common recommendations in the missing data literature. For example, regarding the conduct of sensitivity or bias analysis. So the common recommendation is conduct sensitivity analysis if MNAR is suspected. But using the framework, it can be shown that the complete case analysis is expected to be unbiased under several random mechanisms. Also, that standard implementations of MI are also expected to be unbiased under several of those mechanisms. So, and when you do need them, the design of those sensitivity analyses should be informed by the m-DAG, because there are some arrows that seem problematic, like, for example, exposure causes its own missingness, but they're actually not the reason for the non-recoverability. And this is important because eliciting bias parameters for these bias analysis is really not straightforward. You need to consider elicit expert opinion from several experts, etc. So that's one thing. The other thing is in the inclusion of auxiliary variables in MI, the common recommendation was to include any variable that is associated with incomplete variables and potentially also missingness. But using m-DAGs, we see that certain variables are actually required for unbiased estimation, while other auxiliary variables may introduce bias when they're included in MI because they're colliders. All right, and that's me. I'll just flash some references very quickly, but you have the recordings, so you can go back to them. And that's it. Thank you for listening. I'm really open for any questions.